All right.
Now, the next speaker is Günter Honisch. He is a distinguished engineer from Cisco. He has
You want the tie as well?
26 years of experience in networking, so as old as me at least. And he will try to provide a very interesting overview of where are we going, and actually why are we mixing different technologies on the network to provide a lot of different things to the users. Thanks.
Yeah, welcome. I have a slight problem with our friend Bill. So you see, we converted PowerPoint to a previous version. It got 10 times bigger, and some other things happened. So as a networking company representative, I must like it, because it really increases the traffic. But from a presentation point of view, I rather stick with my own PC. Sorry for this. Yeah, converging networks. What does it mean? There's many meanings of the word converging. The most obvious one, if my remote would work, yeah, is we have those four main areas. So of course data, like we heard in the first presentation, for instance, heavy use, computational use of the network, just plain backup data, all kinds of things going on. And I want to give you a few data points, what we have seen in Cisco when we do our own research, what's going on the desktops. Then the next one, obviously, voice. Voice today is more or less commodity, but still there's a lot to watch out if you deploy voice in your network, and same applies to normal conferencing kind of video. But there's other kinds of video. We mustn't forget in the research community, I guess you're doing maybe telemanipulation, robotics, telesurgery, things like this. And I have totally different requirements for a conference video where I just want to see if my counterpart is male or female, more or less in some cases. Or I cut somebody up and this is the potential killer application finally. So, nasty joke, I know, yeah. But another kind of video, for instance, is surveillance video. So to identify somebody who's trying to rob your canteen in a university or so, you need very high frame rate video. You don't use temporal compression, so you easily end up with 30 megabits per second, and eventually multicast too, because you want a radar storing the video, you want some guard watching it. So video has many faces. Storage also. When we look at storage, I'm going in a little bit more detail there. I didn't tell you what I'm doing in Cisco. I'm not the normal Cisco person, which you believe only works on routers and IP and layer 3 stuff. I'm more from another kind of breed. From my previous company, I worked for Digital many years. I didn't like routers there, I must say, frankly. I learned to live with them at Cisco. But I grew very much up in the switching world. So I still do a lot of large campus layouts, work with universities on their campus deployment, work with many large enterprises, and I do storage. So my main areas are campus and storage, if you have any questions about those. So going in more details here, when we talk about voice, video, data storage, one thing we heard about it at the previous presentations, it's quality of service, it's bandwidth, but it's also high availability. If you want to use voice in a commercial sense, not just to talk to your girlfriend in Australia and having some cheap talk, you're not going to tolerate poor quality. But what's poor quality? That's not so easily defined. I think the IP industry must be very thankful to the cell phone industry. They lowered the expectations so much, so IP could easily jump on and now growing up to high expectations again. So the acceptance was much easier with cell phones. Giving you an idea, when we look at the things you can hear on the phone actually, if you have 1% frame loss rate, and just by statistics, sometimes it's consecutive frame loss, about every 3 minutes you hear it. If you have 0.25% frame loss, you hear it every hour. So we must try to avoid frame loss for voice. It's low speed usually, but you should treat it carefully. Also, we mustn't introduce a delay higher than 150 milliseconds. But 150 milliseconds is mouse-to-ear delay, what we call it. If it's higher, you don't like it. It's walkie-talkie effect. You have collisions talking-wise, not Ethernet-wise. So it's not the comfort you like. And that's the challenge in a network and device design. Not so much in a LAN. In LAN, it's relatively easy. But in the wide area, you need to use all kinds of tricks. So people thought that's challenging. Getting voice 150 milliseconds from A to B, not easy. But what's more challenging? Just a few guesses. Voice is easy compared, except in the wide area. Ever looked at thin client applications like Citrix? Citrix, you type, and your eye gives you the feedback what happens on the screen. So you have a tactile feedback loop. This is more like 70 milliseconds. That's what Citrix specifies. For more advanced tactile feedback, I would rather say we are below 20 milliseconds. More challenging, but not enough yet. What's about storage? How much money do you spend for, let's say, a 5,400 RPM drive? How much money do you spend for a 15,000 RPM drive? The difference is around about 500 to 1,000 euro. What's the performance difference? 5, 10 milliseconds at most. So you don't want to waste this in your network. And this is just if the disk doesn't have it in its local cache. If it really needs to run around and grab the data. If it's in the cache, we're talking about microseconds. So for a network, if you want to deploy storage networked, it means we're in the single-digit milliseconds. If we want to extend fiber channel, and I come to this a little bit later, over the network, we're playing a totally different league. At fiber channel, we're caring about microseconds. We're caring about speed of light issues. And we really have a challenge going more than 100 kilometers even, just because of speed of light issues. So converging networks, from an absolute number point of view, voice is relatively easy. But it gets really challenging at some other applications. When we talk about high availability, there's also a lot of different parameters. As a vendor of networking equipment, I have this discussion very often with customers. And they say, I have a highly available device. It has 2 supervisors in it. It can never fail. You know these arguments? I'm not a salesperson. So if I'm nasty, you know what I could argue? Okay, let's build a switch. Everything is duplicated. What will happen? You're engineers. It breaks twice as often, twice as many parts. Easy. So why do you still buy redundant equipment? Because you hope it's not visible to the end user. And that's the trick from a manufacturer's point of view. Yes, it breaks twice as often. There's no way you can avoid it. Twice as many parts. But your software must be so good, your hardware must be so good to catch those problems before they appear in the network. And that's the whole trick. So it's a real challenge, and I guess there's quite a few engineers, hardware and software engineers in this room. Just think about a processor goes bad, overheats, whatever. What kind of things can happen? A move is no longer a move. An add just calculates wrong. Things you never dreamed about can happen to your software, corrupting structures, tables, but you still need to be able to recover from them. That's the real challenge in talking high availability from a device perspective. When we're talking about network perspective, we're talking about routing protocols, layer 3. We're talking about bridging, layer 2. Giving you one idea, in the early ages of networking, there was something, or is still something, called spanning tree protocol, the classical spanning tree protocol, invented by Radia Perlman, if you know her. At this time, networks were relatively slow. 10 megabit was more than you ever dreamed about. So 50-second convergence time was fine. Just playing safe. Rather make double sure and triple sure. Nothing happens. OK, we do it. But for a gigabit network, for voice over network, for telesurgery, you don't like a 50-second blackout. That's a little bit too long. So something new came along, which is called rapid spanning tree. But rapid spanning tree has sub-second convergence. it's very CPU intensive. It's memory intensive from table maintenance and so on. So many old devices just cannot run rapid spanning tree by software upgrades, even if it's just software. And that's another challenge. The more high availability, the more sophisticated protocols get, the more complex data structures become sometimes, the more compute you need internally in the machine. So it's not easy. Going further, we heard about Gigi is a lot of performance, but I show you in a few minutes, Gigi is easy to eat today with affordable machines, and 10 gig is not far off to be deployed out of a single machine. And this means hungry applications, they eat up your bandwidth. And this is a common misunderstanding that you don't need QS in a campus, you just throw bandwidth on the problem. You know how TCP works. If you throw bandwidth on the problem, TCP uses the bandwidth. It grows as long as the machine can fill the pipe. Finally, you run out of resources at one side. But if you don't have any control on your network, you have a kind of law of the jungle there. And this is not exactly what you want. We heard in the previous presentation a lot about this. And the bigger challenge even is whom to authenticate. Who is trustworthy? Who is important? Who is required? And coming on a few points of this later. And last point, security. We also heard about this already today. You have a lot of very, very clever attacks today. So from a vendor perspective, we need to build in new mechanisms we never considered in the past. So we are just starting now to limit the control plane traffic. You know, have a picture later. Every switch, every router has a kind of brain and a kind of mechanics moving packets forward. And you really want to protect the brain by putting filters which allow only a maximum amount of traffic, malicious traffic, to this kind of important entities. So another challenge from a vendor perspective, if you run secure shell, you run encrypted SNMP version 3. This is all very CPU intense. So if you do a lot of pollings, getting data out of your networking equipment, you need a lot of CPU cycles for those things. It's not for free, but it's absolutely required in a highly available network. This is a slide I stole from Fred Baker. Maybe many of you know him. He was the previous IETF chairman, is doing QS in Cisco. And he pulled it somewhere of his preferred networking points. This is the normal TCP stuff, and the red stuff, as I understood, is mostly Napster, peer-to-peer, and whatever. And many other things are just not identifiable. And I fully agree this is the problem. How can you identify packets which look like web traffic, which hide themselves somehow? And we get asked, this is one of our top priorities. We get asked for this. You mentioned Packeteer. The problem is all those software-based solutions, and we have something called NBAR in this area, they only scale so high. What people ask us, they want a deep lookup. They want a state-based lookup. Really clever stuff at 10 gig speed. And we think it's doable, but not now, not in the next 12 months, let's say. But it needs extremely sophisticated ASIC development, network processors, and a very good compiler algorithm. So lots of research there, so we'd appreciate any inputs if you have them. But it's required. We fully agree. And when we look at the sessions, we see two different worlds. More than 90% are really short stuff. TCP cannot even get up to speed. It's really ping-pong, flying back and forth. But this is really stressful for flow-based components in the network. If you have a router or a switch which works on a flow-by-flow base, software-based eventually, this drives the CPU to its limits. If you have a server load balancer, anybody knows how a server load balancer works? Basically, you spoof a server to the client, say, I am the web server. You make the TCP connection. Give me your URL. When you have the URL, then you look at the other side, talking to a server, you're up, okay. Then you have two TCP connections. Finally, you, the switch, splice them together, correct the sequence numbers and things like this. So you can imagine, for short flows, a lot of work just for a few packets. The other side is the heavy traffic, the massive amounts, backup, file copies. So most of the traffic, byte-wise, comes from less than 10% of the sessions. And here we observe extremely high rate bursts. And some of those flows are extremely aggressive. You cannot control them with the usual TCP mechanisms. They just don't react because they are written bad, they are done on purpose, or they are network fault. What happens if you have a spanning tree loop? You get the most aggressive flow you can imagine. And of course it doesn't react to anything because it's a broken network. So there's just some things which don't have a graceful behavior. And from an equipment perspective, it's difficult. How can I control some aggressive flows and help some less aggressive flows? So I need a flow-based kind of quality of service, which is very difficult to make in hardware. Hardware designers try to avoid to have too much state in hardware. This doesn't scale. At some points in the network you can do it. For instance, we have a mid-range switch, which is more at smaller and networks and wiring closets. There we have a flow-based buffer management. It's called dynamic buffer limiting. So aggressive flows, we watch them a few moments, and then we say, you're not well behaving. You don't get more buffers than the absolute minimum. So it's possible, but it's always a scaling issue. At really high-end devices in the hundreds of gigabit range, no way you can do this. And why do we need those high speeds at all? And so we did some research that was from our IT department. Actually, they wanted to know if it's worthwhile deploying gigabit to all our desktops internally. And what we did, we bought a few normal machines. So we just went to the electronic shops, bought some Intel-based machines for a simple reason. It's less a CPU issue, it's more a chipset issue. The newest Intel chipsets have what's called LAN on motherboard, LAM. And the newest LAM implementations are no longer connected to a virtual PCI, they are directly on an internal memory bus, also the disks. And with those kinds of chipsets, you easily get 950 megabit per second out of a desktop machine. And with some CPU impact, but it comes out with a 2.4 gig Pentium 4. If you don't want the CPU impact, you buy something else, which is called an offloading NIC, TCP offload. And this has a hardware accelerator on the NIC card. And there with very low CPU utilization, you go also close to a gigabit performance. So we inserted a software shim, which logged what's going on during the day. And we were able to replay those things. And what we have seen, there's tremendous performance differences. For instance, the 1 gig backup, 10 seconds versus 85 seconds. So this makes a big issue. If you deploy Outlook on your desktops, you have these lovely PST files. You look at one email and 1 gig changed. So this is one of the main reasons we're looking into this, by the way. And also at normal applications. So there's a good reason going to gigabit on a desktop. But be aware, if one guy creates a misbehaving application, you get a gigabit misbehaving out of a single desktop. But on the other side, I have to say, in the normal office kind of environment, we had engineers, we had secretaries, all kinds of people mixed here. The average data amount was 2 to 4 gigabytes a day. So if you look at the duty cycle, it's extremely low. You have 900 plus megabit speed, but only for a few seconds. So if you make a quick and dirty calculation, it's a few minutes full speed per day, per desk. It's not more. You can make the calculation yourself. Look how much data you transfer during a day. It's not that much, usually. But I'm careful. You are a different breed. You run in grid computing, you run a lot of research. So it could be that you move terabytes a day. But for the normal average desktop, it's not much. So this teaches us one thing. For a normal desktop, you can heavily oversubscribe the switching infrastructure because you have this extremely low duty cycle. For research, grid computing, I wouldn't do it. So you need to know what you're doing at your desktops. And when we talk about no QoS at gigabit speeds required, another test we did briefly, if you have two servers in a kind of Y fashion going to a third one, and we do TCP from one and UDP from the other one, You see TCP is going happily along at nearly 900 megabits per second. Then UDP comes along, TCP crashes down to nothing. UDP wins because it doesn't react to flow control until it ends again. Then TCP ramps up. But UDP also got some hit. UDP lost at least some frames. UDP had a lot of consecutive losses. So it wasn't a good behavior for both of them. And that's what I mean. You need mechanisms who get you more fairness between. You need extremely well-designed buffering. And speed alone doesn't help if the machines and the applications raise the same value. And one typical thing I briefly touch here is storage over IP. There's 3 variants of it. The most obvious, everybody of you know, is file services. And file services is, since many years, you're serving a file system by NFS, by DEFs, whatever you like. So it's file-based access. This doesn't work well for databases. This doesn't work well or is not supported for Microsoft Exchange. For those applications, you need block-based access. So usually, in the data center, you have a SAN, which is a fibers channel network, bringing the disks block by block to your SCSI kind of device driver, to your file system in the machine. What is new here, this was developed by IBM together with Cisco, and actually one of our vice presidents had the idea. They still do technical stuff. It's called iSCSI. And iSCSI is nothing else but you take the SCSI data off from a fiber channel, put it in TCP, and run it over the network. But that means the characteristics of an I/O network, like SCSI or fiber channel, is suddenly put on an IP network. So you have the demands of quality of service. And I can only tell you our numbers. The switch we're using for this can deliver about 8 gigabit of iSCSI per slot. So there's quite a few slots, so you can easily go to, let's say, 40 gigabits iSCSI on your network. That's no fundamental problem. On the other side, who eats the iSCSI? This is, let's say, a server running Exchange, running some Oracle application somewhere in a department off from the big disk farms. And Intel proposes in about 12 months' time, they will have offloading 10 gigadapters doing about 7 gig per system. So you can expect quite high performance storage applications across your network. Not that far away. And fiber channel over IP is just tunneling fiber channel to fiber channel, and here we have all the speed of light issues and things like this I mentioned already. So it's again an I/O channel which you can extend to some amount but not indefinitely. So when I wrap all those things together now, in a typical campus environment, we require, of course, very high speeds. We have new traffic patterns like iSCSI. And iSCSI, when we talk about security, needs authentication too. So iSCSI works with radios. Yes, all those things is done. It's in the standards. And grid computing, even in normal enterprises, it takes off now. Lots of banks and insurances are considering it. And the offloading NICs together, we get new amounts of data. So for us, it's clear. GigE to the desktop is the new thing. It's just being deployed right now. Then the question is, how much backbone speed do you use usually? It will be order of magnitude more, 10 gig or multiple 10 gigs. And the challenge is then, in the wide area, in many countries, it's still expensive. So you have everything from ISDN to 10 gig. So from big bottleneck to no bottleneck at all. Another challenge, and this was mentioned already, is multicast. Besides authentication, billing, all those things, which, yes, it's a challenge, having a highly available multicast is also a challenge. If you're running multicast, just rip out your rendezvous point, doing part of your multicast structure in the network, and then count seconds. Depending on your software setup, on the vendor, on the protocol you're using, it's at a big multicast network, which many of you run maybe, it's a couple of seconds to a couple of years. That's the variant you have here. We didn't wait a couple of years, we rebooted before. But I mean, multicast is the biggest variant between vendors' protocols implementation today. I would say nothing else varies that much if you look into differences. And finally, I talked about quality of service. Even in high-speed environments, you need to do some quality of service because everything gets fast so quickly, we need to watch it out. And, important point, how can I be sure that this application is a telephone or an authenticated high-speed user? We think the big solution is 802.1x, which is authentication from a user, from a device perspective. So from Cisco, I can only say we are going to deploy it in all our devices. Telephones will get it. We know from HP they will put it in the print servers. So I believe very much each and every appliance over the coming years will authenticate itself, and then you can trust it's this device, it's this user, and apply the right amount of services to this spot. But it takes another 1 or 2 years until everybody has it, hopefully. When we talk about network components the last couple of minutes, I mentioned already, you have a brain and you have some mechanism moving data, manipulating data. And often I get asked by customer discussions, is a bus architecture, a crossbar architecture, a shared memory architecture, what's better? What shall I say? It depends. That's the usual answer. So again, from a Cisco point of view, we have devices for each of those things. From a pure technical sense, actually bus architecture is the best one. Problem is it doesn't scale indefinitely high. Shared memory has the same issue. It's perfect for buffer management like many other things, but it doesn't go up that high as we want it. So finally, for the extreme high end of devices, you end up with crossbar, which give you all kinds of challenges. And I'm going to give you just one of the many parameters we see between glossy brochure performance and real-world performance. And finally, when we talk about QoS, it's not the number of queues. That's an easy thing, yes. But more important is how does congestion control work? Do you have something like RAID, weighted RAID, flow RAID? How are the buffers allocated? How are they managed? So the problem, if you just look at the surface, at the tip of the iceberg, it's easy. But the deeper you dive, the more you need to know about all those things, and you are the right community actually diving deeper. But please look left and right and give you some hints. So one discussion I often have with people when we talk about architectures, concentrate on 3 numbers. How fast, how many queues, and how low the price is. That's the usual discussion. I guess you know it. And then I spent 2 hours explaining there's something else. Something else which maybe many of you never cared, never heard about, and just think a few minutes about those things. Maybe you still don't care afterward, but at least you heard about it. For instance, a parameter flows per second, or how long you need to debug some stuff. That's hard to quantify. The only thing I can somewhat quantify easily in a few minutes is what's flow-based, what's flow per second. Give you one idea. Let's assume a hypothetical device, a switch, central CPU, line cards with local caches, local buffers, and happily going along, moving traffic, routing. Then something happens. You mentioned you like to decode a network. Maybe somebody does it. You have a flap. Your main trunk is gone. That means all routes have to be recalculated. You know, this means the OSPF Dijkstra calculations, heavy CPU. All the caches are wiped out because the topology changed. So every flow coming along needs to go to the CPU, need to come back, being programmed in hardware. That's good if it's a 10 million packet flow. If it's a 10 packet flow, not good, because you have lots of interrupts to the CPU. Now assume another hypothetical device based on a different architecture. You have a route table, same thing again, but you convert it to a hardware-friendly forwarding database, put it in hardware, and have an internal multicast in the backplane putting on each and every line card. And if you have a route table flap, you couldn't care less what's going on here. You calculate your route table, you forward it to the hardware, and each frame coming along is forwarded to the right spot. It never goes to the CPU for any normal forwarding thing. And some vendors have this implementation, some vendors have that implementation. And the difference is obvious. If you have the typical, not an artificial Tolly test traffic, I have to say this, sorry. If you have a typical network traffic out on an internet, this usually burns your CPU away after route flip, takes forever to come up again. This is up in a matter of seconds. So again, you have both implemented at different vendors, but you can see this is a very important parameter if it goes for real-world performance. After, let's say, 5 minutes, both have the same performance if you have long-lived flows, which tests usually have. But at short-lived flows, it can never, ever scale to this amount. So just one of the many architectural decisions we make. And giving you some more insight, what's the trade-off? You need very special, rather expensive chips to do it. They're called ternary CAMs, which is a content associative memory. The trick is, normally if you do a table search, you know in software, you search, search, search until you find through. This is a chip, you ask it for a certain match, and it comes back the next cycle, clock cycle. This is the best hit I got. So you have, no matter how big the table is, you have the same lookup time every time. But those things are expensive, hot, power hungry, so you have limitations applying them. When we look further, what else can we do in networking devices? The holy grail often is network processors. Great stuff. Fast, you can have short development cycle, you can change sync, but it's not all pink and glossy. You can very difficultly predict the performance before you build it, before you program it. And I'm now about 25 years in IT and data communications. I have never seen a device which has memory left after it was shipped. I have never seen a device which had spare cycles left with a network processor. That seems to be a rule of engineering. So whenever you do it, you use up all your resources. But it has advantages. So we use them heavily in intelligent wide area kind of cards up to, let's say, 10 gigabit speeds. It's possible, yes. But they don't solve all the problems. They're still challenging. Another way of doing it, you develop your own silicon. And just giving you an idea, one of our mid-range, it's not the high-end stuff, it's a mid-range switch we have. The one switching ASIC, two switching ASICs, is twice as complex as a Pentium 4. And that's not cheap stuff. You don't have the numbers shipping as a Pentium 4. And it takes you about 18 to 24 months to develop it. And if you make a mistake, 6 months back. So this is something you bet a lot on, a piece of silicon. And at all of those things, we are reaching certain limits. This is a slide I stole from Intel, and I really like it. This shows one of the barriers we're encountering. When people ask, I got this question from another research community just a couple of weeks back, why you don't put 2 10 gig interfaces on the supervisor? Easy answer. Then we end up somewhere here, and this doesn't work well with air-cooled devices. And water-cooled switches are not that famous, I guess. That's the problem we have. In networking, we are really at the heat barrier. I think all manufacturers are there right now. So we do extensive simulations about the heat distribution and airflows in each and every slot. That's really the limit we have right now. We have to wait for another generation of ASICs going down to smaller silicon, then we can put some more in it. Because I'm often asked, what's about the next speed? When do we have 40, 80, 100 gig? Yeah, that's the answer. Either you have slots that big, water-cooled, or we have to wait one more generation often to fit it in. And this is the expectation from a converged network. I like this slide because it shows really what people expect out of networking. The mobility of GSM, some behavior of the ATM, bandwidth of an optical network. There's hope. We're getting there. But one common misunderstanding, just the last 2 slides on this. Many people believe Ethernet, that's the solution. It will do everything. But be careful. Ethernet is a frame format. Ethernet is nothing. Ethernet could be run by spanning tree, 50 seconds. Fast spanning tree, less than 1 second. A crappy OSPF, a good OSPF. You have so many variants of Ethernet. You cannot say Ethernet is good or bad. Ethernet has this quality of service. It's all implementation, all deployment. So be really careful when you say Ethernet can do this or that. You need always to say Ethernet with this routing protocol, with this quality of service, with this, and this. It's much more difficult to specify than ATM in the past. And it's not so easy as it looks first. So, and one of the other projects which fit in here in convergence, just very briefly touch it. If you have any more questions about this, there's Peter Tomso, a colleague of mine here, who works mainly with the research community on this. So we're thinking that in a real converged world, IP, by means of MPLS, should also control the optical plane, all the lambdas, all the optical switching. But this is something where there's big fights in the industry all over. And it's not something the research community cares a lot, but in the service provider world, money is tight. So all the greenfield carriers are rather brownfield carriers right now. They don't do well, and they try to keep their stuff somehow going and don't like to invest in great new technologies. That's why we see this in a lot of research networks, in some telecom networks, but let's see how it goes along. That's some other work we're doing. I not have the time going through it. So we're really doing work getting normal ISIS routing, for instance, in the sub-100 millisecond convergence. But it's all work. You really do table tuning. You do a lot of nitty-gritty detail inside your code to go down, down, down until you have the fast convergence like a SDH network. So this is other work we do. If you have interest, there are papers, research papers available on this. To wrap it up, the convergence has happened, but it didn't stop yet. So many companies ripped out the normal PBX, have some kind of an IP-based phone system. Storage is just being integrated. It's beginning now. The standard is out a month or so. MPLS is the most integrating technology. We see MPLS also deployed in the campus more and more in the future. We see VPNs deployed in the campus because of security reasons. The previous presentation made perfect sense to many of the ideas we have. So you need to separate users. You cannot have access control lists at all points of the network. You need to separate them and have 2 points of connectivity, things like this. Ethernet in the many flavors will be dominant. And that's the point I just make, that many service provider features will come to enterprises, universities, campus environments. So that's all I could say in about 25 minutes. Thank you for your time.
Yes.
Hi. As you come from Cisco, you nicely avoid storage area routers 6500. Can you tell us more about that?
What kind of storage and 6500 is totally different animals. Our storage switches, they look like a 6500, but the only thing in common is the power supply and some ASICs, yes. But the storage switches are pure fiber channel switches, built from ground up, greenfield, based on a Linux operating system with POSIX-compliant APIs, running other vendors' application inside, totally different beasts. 6500 in its heart is an Ethernet GigE, 10 GigE switch. Depends what you make out of it. You fill it with firewalls, it's a super firewall. You fill it with Ethernet modules, it's an Ethernet switch. You fill it with wide area modules, it's a router. So it's very difficult saying a general statement about those things. It's really what you fit in it. Then we can talk in detail. Sorry to be that generic, but it's two different beasts.
I have a question. Scalability is obviously one of the issues. Just yesterday we talked about grid applications and so on, and the main point is that they are developing new application in which a single application spawns many flow at the same time. So it is equivalent to have to scale from 100 to 1,000 users, or scale to staying at 100 users, having 10,000 flows. I mean, the network will behave in the same way, or do we need to do things in a different way? Because the number of flows is...
Let's say all our switches, except I have to name a product, our 6500 with the sub 1A. That's the only flow-based device we still have for wiring closets. Everything else is completely flow independent. You have 1 packet flows or 1 million packet flows, it has the same performance. It's all topology-based forwarding. So we make a topology-based table, and it doesn't matter how long a flow is. This is the switching answer. For firewalls, load balancing, all the other things, yes, that's a different world. But switching and routing, with this one exception, is all based on topology-based forwarding. This is not the case at many other vendors, but I don't talk about this in public, so if you have questions, please see me.
Any other question? Okay, thanks for all these food for thought, and thanks again to the speakers.